Section 11.5 is alternating series. The convergence test that we just looked at only applies to series with positive terms. So if you go back and you look at all those examples that we did, all the terms in that series were positive. This section we learned how to deal with series who have terms that are alternating in sign. So alternating series is a series whose terms alternate in sign, sometimes containing -1 to an nth power or -1 to an n-1 power, or trigonometric functions. For example, the sum from n equals 1 to infinity of -1 to the n-1 of 1 over n will be equal to, and if you were to substitute in 1, you get -1 to the 0 power times 1 over 1, or just 1. Next, if you substitute in 2, you'll have a -1 times 1/2, so -1/2. Continuing this on, you'll notice that it goes to being +1/3, then -1/4, then +1/5, and so on. So the top of page 16 says the alternating series test. And this says that if the alternating series, the sum from n equals 1 to infinity of -1 to the n-1 times b sub n equals b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus and so on, and b sub n is greater than 0. And notice what b sub n is. B sub n does not include that part that is the -1. And so b sub n is the other part would be satisfying the following conditions. So 1, it says that b sub n plus 1 is less than or equal to b sub n for all n. And so this means that it is decreasing. And sometimes this is easy to tell, but sometimes it's difficult to tell. So if it's unclear, use the first derivative test. And we saw this with the integral test earlier a few sections ago about showing if something is decreasing. And then 2 says the limit as n approaches infinity of b sub n equals 0. Then the series will be convergent. So the first example on here says test the series for convergence or divergence. And so noticing that this has alternating signs between terms, I'm aware of the fact that this possibly could be an alternating series test that I'd be using to show that it's convergent or divergent. So in order to do that, I need to figure out a formula to rewrite this in summation notation to find that b sub n. And so looking at it, I notice that the numerator is all the same. It's always a 2. And for the denominator, just looking at the denominator, I am, besides the minus signs, I'm adding 2 to go from 3 to 5. From 5 to 7, I add 2. 7 to 9, I add 2. And 9 to 11, I add 2. Again, I notice that it's alternating signs in addition, but that will be dealing with a -1 to a power. So for the denominator, I notice that it is a arithmetic sequence, and so a sub n equals, and it's a1 plus n-1 times d, that common difference that we have, which is times 2. And then this simplifies to being 2n plus 1. And you can definitely sit there and substitute in different values. Like if you were to substitute in 1, you'll get 3. Substitute in 2, you get 5. Substitute in 3, you get 7. Substitute in 4, you get 9, and so on. And so I can rewrite this as the series, the sum from n equals 1 to infinity of, and I'm going to have a -1 raised to some power. And I noticed that my first term is positive, so I can't have it raised to the nth power because raising it to the nth power would make that first term be negative. So you can either add 1 or subtract 1, so I'm going to go ahead and just put a +1 here. And then times my function, which is going to be 2 in the numerator, over, and then 2n plus 1. And again, you can always check this by substituting in the different values of n. So substituting n, make sure that we get 2/3. Substituting in n is 2 and making sure that we get 2/5 and it's negative. and so on. So our b sub n is equal to 2 over 2n plus 1. And these are all positive values. If you notice, this would be greater than 0 for all n. And then we have to check that the following conditions are satisfied. The first one is that it's decreasing. And so you can think about this and show this and say b sub n plus 1, which would be equal to 2 over 2 times n plus 1, which is equal to 2 over, and that would be 2n plus 3. And this is less than or equal to 2 over 2n plus 1, which was equal to our b sub n. So check, this is decreasing. And then the second thing that we need to show is that the limit as n approaches infinity of b sub n is equal to 0. So we have the limit as n approaches infinity of b sub n, which for us is 2 over 2n plus 1. And as I take my limit, I notice that that denominator is getting a lot larger as n is approaching infinity, and this would be equal to 0. So check, that's our second thing. And so therefore, since those two conditions are satisfied and that b sub n is greater than 0, we can say that therefore the series, which is 2/3 minus 2/5 plus 2/7 minus 2/9, and I'll just say plus, 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 on and on, is convergent. By the alternating series test. So again, a couple things to note. One is that you do need to make sure that whenever you put convergent or divergent, you're writing a reason why, what test you were using. And the other thing is to note that you need to show and verify that all the conditions are met for any of these tests. And for the alternating series test, it had to be that b sub n is greater than 0, and we did have that stated up above. And then it had to be a decreasing function, which we stated in part 1. In part 2, we showed that the limit is equal to 0, and therefore we can conclude that by the alternating series test that this converges. Part B is written in summation notation, and this one says the sum from n equals 1 to infinity of -1 to the nth times n over the square root of n cubed plus 2. And so for this b sub n, we can tell is just going to be equal to n over the square root of n cubed plus 2. And all of these terms are going to be greater than 0, so for all n. So that was the first thing that we had to check. And then number 1, we have to check to see that it is decreasing. And so we know that b sub n plus 1 is equal to n plus 1 over the square root of n plus 1 cubed plus 2. And it's difficult to conclude that it's decreasing. You could say that that denominator is growing faster than the numerator. So therefore each term would be consecutively decreasing. But I'm going to go ahead and say that this one's very unclear. And so if it's unclear to show, it's unclear that b sub n plus 1 is less than or equal to b sub n, or that it's decreasing, then that means that we're going to use our first derivative test. And so we'll go ahead and say, so f of x equals our b sub n, but we're going to write that with x's, and we have x over the square root of x cubed plus 2. And so our first derivative, using the quotient rule, chain rule, we're going to end up with a numerator of and it's going to be the bottom, which I'm going to write as x cubed plus 2 to the 1/2, times the derivative of the top, which is just 1, minus the top, times the derivative of the denominator, which is going to be 1/2 x cubed plus 2 to the negative 1/2, times the derivative of the inside, which is going to be 3x squared, all over the denominator squared. And so from here, we're able to clean this up. I noticed that both of these terms have a x cubed plus 2 to a power. And so I'm going to go ahead and factor out the smaller one, which would be x cubed plus 2 to the 1/2. And I'm also going to factor out the 1/2, just so I don't have to deal with any fractions with simplifying. So I have x cubed plus 2 to the negative 1/2. So then left over, I took out a negative 1/2, so that would be x cubed plus 2 to the positive 1. And I also have a 2 because I technically took a 1/2 out, so I would need to put a 2. And that's raised to the first. And then minus, and then left over in the second term, we have a 3x squared and a x. And so we're going to have minus 3x to the third, all over, and we have x cubed plus 2. If that numerator is bothering you, you can always check it by distributing it back through to see that it matches. So from here, we're able to simplify again. And I'm going to go ahead and put the 2 from my 1/2 in the denominator, and then also move the x cubed plus 2 to the negative 1/2 to the denominator. And so our denominator is now going to be 2 times x cubed plus 2 to the 3 over 2, since I already had 1 down here, and I moved a 1/2 down in the denominator also. The numerator is going to simplify to 2x cubed plus 4 minus 3x cubed, or just 4 minus x cubed. And we need to see that this is going to be decreasing or less than 0. And so in order to do that, the denominator is always going to be positive. So that means that the numerator would have to be less than 0, which means that we'd have 4 is less than x cubed. Or taking the cube root of both sides, we'd have x is greater than the cube root of 4, which is equal to 1.59. And so it is decreasing on values after 1.59. And since n for our values are going to be whole numbers, we're going to say this is going to be decreasing from 2 to infinity. And so it's decreasing on, and it doesn't decrease over just that piece, but decreasing for all of our n. We would say that this is, in general, going to be a decreasing function. And then 2, the second thing that we need to show is that the limit as n approaches infinity of our function, which is n over the square root of n cubed plus 2. And you have a couple different ways to do this, but we need to show that this is equal to 0. And so I'm going to go ahead and rewrite this as the limit as n approaches infinity. And I'm going to say the square root of n squared over the square root of n cubed plus 2. And the reason why I did this is so that way the numerator would also have a square root, and then I could rewrite this as the limit as n approaches infinity of the square root of n squared over n cubed plus 2. So we have an indeterminate function like we saw at the very beginning, even before we simplified this. This was equal to infinity over infinity, and we knew that this is indeterminate. And so we learned that to deal with indeterminate functions, we're going to multiply by the degree in the denominator, which is going to be 1 over n to the third, or divide every single term by that. And when we do this, we're going to have the limit as n approaches infinity of, and it's going to be the square root of, we're going to have 1 over n all over 1 plus 2 over n cubed. And so from here, as we take the limit, you'll notice that our numerator is going to 0. And the denominator, the term 2 over n cubed, would also be going to 0. And so we have the square root of 0 over 1 plus 0, which would just equal to 0. And so we were needing to show the limit as n approaches infinity of b sub n is equal to 0, and it does. So that's our check. And so therefore, we can say the sum from n equals 1 to infinity of our original function, which was negative 1 to the n, times n over the square root of n cubed plus 2 is convergent. And this is by the alternating series test. We have 2 more examples of this on the next page, and I'm going to go ahead and circle both of these, and we'll look at these 2 together in class. And then on the bottom of the page, it says the alternating series estimation theorem. So if S equals the sum of negative 1 to the n minus 1 times b sub n is the sum of alternating series that satisfies those 2 conditions that we saw earlier, that's decreasing, and that the limit as n approaches infinity of b sub n equals 0, then the absolute value of r sub n, which again was that remainder, is equal to the absolute value of s minus s sub n, which is less than or equal to b sub n plus 1. And so b sub n plus 1 is going to be, the error is at most the size of the first neglected term. So if we had, say, b1 minus b2 plus b3 minus b4 plus b5, minus and going on forever, and we were to say that this is correct to an error within correct within an error of at most, and it would be that following term, which is going to be the absolute value of negative b to the fourth, or b to the fourth. And so b to the fourth right here, this is our first neglected term. The example on the next page says, show that the series is convergent. How many terms of the series do we need to add to find the sum to the indicated accuracy? And so the first example is, and the series is the sum from n equals 1 to infinity of negative 1 to the nth all over n times 5 to the nth, and we want an error less than 0.0001. So first thing we need to do is show that it's convergent, and so in order to do that, we're going to say b sub n is equal to just 1 over n times 5 to the n, which is greater than 0 for all n. Then we have 2 things that we need to show since this is an alternating series. First one is going to be that it is decreasing, and so hopefully you can see that b sub n plus 1, which is equal to 1 over n plus 1 times 5 to the n plus 1. Would be less than 1 over n times 5 to the n, which is equal to b sub n. So check, it is decreasing. Second thing is that the limit as n approaches infinity of b sub n, which is 1 over n times 5 to the n, is going to be equal to 0. And in this case, since that denominator is growing to infinity, 1 over something really large would be equal to 0. So check. So we can say, therefore, the original series that we have, which is from n equals 1 to infinity, of negative 1 to the nth, all over n times 5 to the n, converges. And this is because of the alternating series test. So again, making sure to show that it is convergent. The next thing says, how many terms of the series do we need to add to find the sum to the indicated accuracy? And that accuracy is stated here. And so I'm going to make a little table here to show and see what the sum would be as we go. And so we have n and we have b sub n. And so first term, second term, and third term, we'll keep adding on as we go. So the first term for b sub n, I get 0.2. The second term, when you substitute this into b, you get 1 over 2 times 5 to the second, which is 0.02. That third term is going to be 0.00267. So as we're adding these together and getting our sum, you'll notice that so far these values are all greater than 0.0001. So these are changing that sum within this bound, and so I still need to keep going. So let me look at the fourth term. And when I do plug in 4, I have 1 over 4 to the 5 to the fourth power. And this is going to be 0.0004, which is close to that error that we need to be in between. It needs to be less than 0.0001. So this one is also greater than 0.0001. So let's look at the fifth term. In the fifth term, if I have 1 over 5 times 5 to the fifth power, I get 0.000064, and this is less than 0.0001, which is that error. And so, therefore, by the alternating series estimation theorem, as stated at the bottom of the previous page, n is equal to 4. And so stating this in words, this is because if you add the first 4 terms to get the sum to desired accuracy, since the fifth term is less than that desired accuracy, we need to add the first 4 terms to get to the sum of the desired accuracy. So again, adding those first 4 terms gets to some of the desired accuracy. After that, it's affecting more precise accuracy. And so since the fifth term is less than that desired accuracy, we need to add the first 4 terms to get the sum of the desired accuracy. The example right below says to approximate the sum of the series correct to the 4th decimal place. And so for this, we have the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n to the 6th. And I first need to show that this converges. And so in order to do that, I'm going to say b sub n is equal to 1 over n to the 6th, which is greater than 0 for all n. And then the 2 things that we need to check is that it's decreasing, and hopefully we can see that 1 over n plus 1 to the 6 is going to be less than or equal to 1 over n to the 6th. And so therefore, which is b to the n, and this one was b to the n plus 1. So check, it is decreasing. Second thing that we need to look at is the limit as n approaches infinity of 1 over n to the 6th. And 1 over something large would be going off to 0, so check. So we can say that therefore the sum from n equals 1 to infinity of negative 1 to the n plus 1 all over n to the 6th converges by the alternating series test. So the next thing that we're going to do is to approximate the sum of the series correct to 4 decimal places. I'm not sure how many terms I'm going to need, so I'm going to need to make a table that I can keep adding to until I get to that desired value. So I'm going to have n here. I'm also going to write a sub n, and remember again, a sub n is this function over here that you were given, -1 to the n plus 1 divided by n to the 6th. And I'm going to write down what I get for those terms, and then in addition to that, I'm going to make another column over here that's going to be my sum, and I'm going to just call that s sub n. So the first term, if you plug in 1, the first term that we get is 1, and so that sum would be 1 also. The second term that we get is -0.0156, and so adding that together with the previous term, we get a sum of 0.9844. The third term that we have, if you substitute in 3, you're going to get 0.0014, and again, your sum of those first 3 terms, adding that up, is 0.9858. And so far this is correct only to 2 decimal places. You'll notice that it's not moving. The 9.98 is the same, but the third decimal place is changing. So I need to go ahead and do 4. So subbing in 4 into to get the fourth term, we get point, and this is a -0.000, and it's 24. And then adding up all these terms, we get 0.9855. And I'm just going to round this to the 4th decimal place for my sum, since that was what it was saying up above. This is now correct to 3 decimal places. So I'm going to try another one and maybe we'll be done. And if not, then I will have to keep going. So my 5th term is going to be positive, and it's 0.000064. And adding this in, we get 0.9856. So it's getting closer. And so if we look at the 6th term, we have, this is a -0 point, and then we have 0.0000, and it's 21. And adding this in for our sum, we get 0.9855. So still not correct yet. So I'm going to go ahead and continue this on. And so we have 7th term, and for this we get 0.000085, and then our sum of these terms would be 0.9856. So going again with the 8th term, we get -0.000038, and adding this in, we have a sum of 0.9855. And it looks like right now it's just bouncing between those two, so hopefully we are close and it's converging. Again, it's alternating, so that's causing this not to converge as fast. So then our 9th term that we have is going to be 0.000019, and adding this in, we get 0.9856. So again, hopefully one more term. 10th term now is going to be a -0.000001, and adding this term in to our sum, we get 0.9856, and so this doesn't change the 4th decimal place. We finally found it, so doesn't change 4th decimal place. And so therefore, we can say that the sum from n equals 1, and we're going out to the 9th term is as far as we would have to go because the 10th term isn't changing it, of negative 1 to the n plus 1 all over n to the 6 is approximately going to be equal to 0.9856. That would be our approximation, correct out to 4 decimal places.